Good morning. This is the e-learning day lesson for April 8th, section 14.1, covering limits of functions. So again, when you think about a limit, think about the end or the farthest that something goes. Right? So if you consider a polygon with n sides, right? So now we know that we can't start off a polygon with one side or two sides. We need a minimum of three-sided polygons. So if n is equal to 3, right, we know, okay, three sides means, right, we're looking at a triangle. Right? If n equals 4, we know we have a quadrilateral. N equals 5, we have a pentagon. 2, 3, 4, 5. Right, and so on, right, we go to n equals 8, it's an octagon, 1, 2, 3, 4, 5, 6, 7, 8. Right. So now you see, as the more sides we add, right, more sides that we have to draw here, right, our polygon shape changes. Right, so if you imagine, right, if we went to 100 sides, right, what that shape would look like. Well, again, if we take a look at the pattern, as we increase the number of sides, we figure that, hey, the more sides we add, right, we're going to have to be able to draw this in such a way where we're connecting all these sides, right? So if we're thinking about, hey, if we are setting the limit, if n went to infinity, right, some really big number of this n-sided polygon, right, what sort of shape would we end up with? Well, we would start to be looking at something that looks almost like a circle, right? The more sides we added, right? If we had like a shape polygon that had 1,000 sides, right? We would almost get to look very much like a circle. Right? Now we know that it wouldn't actually be a circle, because for a polygon you'd have to have flat sides, but again, just the view of it, hey, it looks like as we get to some figure that has a really large number of sides, it starts to look like a circle. Now let's look at the sequence. All right, so here is an expression that is describing a sequence. All right, so if we look at the first term, right, we plug 1 in for n, I get 1/2. Right, the second term, plug 2 in for n, 2/3. The third term, 3 in for n, we get 3/4. Right. I skip all the way to maybe the 10th term. Right, the value of the 10th term would be, plug 10 in for n, I get 10/11. If I skipped all the way over to the 1,000th term, the value of the 1,000th term defined by this expression would be 1,000/1,001. Alright, if I skipped all the way to the 1,000,000th term, plug 1,000,000 in for n, one too many zeros, I think. That's right. This is what we'd end up with. Right. So what are you noticing? Well, again, when we start with our first term, we get a value of 1/2. Second term is 2/3, 3/4. As n gets really, really big, right, this difference of 1 between the numerator and the denominator almost becomes irrelevant. Right? What's happening as n gets really, really big, right? Hey, the limit, as n goes to some really big number, like infinity, for this expression, right, it's bringing us to a value of 1. Right? Now, we know it's not going to be exactly 1, but we're getting closer and closer to 1 as that n value increases to some really big number, right? This 1, again, becomes irrelevant. Take a look at this sequence. All right, we plot for the first term, we have 1 over 1 or just 1. The second term, 1/2, right? Find the third term, plug 3 in for n, I get 1/3. All right, we skip over to the 10th term, plug 10 in for n. Right, do we see where this sequence is going, what the limit is as we get to some, as the value of n gets to be really big? All right, if I went over to the 50,000th term, what's happening? Well, as we move from one term to the next, as the term number increases, the value of the term is getting smaller and smaller and smaller, to the point where, hey, as n gets to some really huge number, infinity, right, this expression is getting closer and closer to 0. Right? And as these numbers get smaller, right, we can only go to one place. Right? Now, we know we're never going to hit 0. Right? There's no way that this expression is ever going to equal 0 exactly. Right? But that's where it's headed. Right? When we think about a limit, it's not necessarily what it's going to be when n is infinity. It's like, hey, as n gets bigger and bigger, what does it look like we're headed towards? Right? The polygon example, right? The more size we add, hey, that shape is starting to look more and more like a circle, but it will never get there. We know that, right? For this expression, as we go from one term to the next, as that term value gets bigger, right? This value we're approaching is approaching some value really close to 1. We know we're never going to get there. Same thing with this expression. Okay, so we want to make sure we understand, hey, when it comes to limits, all right, it's not necessarily about, hey, what is the end result? What is the final destination? Sometimes it's about, hey, what are we headed towards? What does it look like, right, is coming at the end of the tunnel? Okay. Now, typically we find limits of functions. So let's consider this function as a little notation typo here, right? F of x is equal to 1 over x. So again, when you graph this in your calculator, right, the graph is going to look something like this. Right, this is the graph of function 1 over x. Okay, so like when x is 1, we know we plug 1 in for x, the output is 1. Right, when I plug 2 in for x, the output is 1/2. Okay? So again, this is the graph for 1 over x. So when we want to find the limit of this function as x goes to positive infinity, right? Again, we're not necessarily looking for what is the end value, but what does it look like it's headed towards, right? So as x goes to positive infinity for this function, right, again, so we're looking at our graph, and so here is a part of the graph. We talked about end behavior earlier this year. Okay, where does it look like this graph is headed towards? Well, as x gets bigger and bigger and bigger, right, the value of our function gets smaller and smaller and smaller. Right? And how small does it go? Well, it's approaching 0. Again, we know from our previous studies that this is never going to cross the x-axis. It's getting closer and closer to the x-axis, meaning the output of the function is getting closer and closer to 0. So that's our limit. Right? Our function values are approaching 0 as x goes to positive infinity. finding the limit of this function as x goes to negative infinity. Okay, so we're looking at our graph, and okay, so we're looking at this part of our graph because this is the only part of the graph that has our x values going to negative infinity. So again, what's happening here is our output values are growing. Right, they're starting from a really negative place, and it's growing to the point where it's approaching 0. Right, the limit of our function as x goes to negative infinity is 0. About the limit of this function as x approaches 2. So we don't always have to be about infinity. We want to approach it to a specific value. Well, here's 2 on our graph. Okay, so whether we're approaching 2 from the left or from the right, we are going to end up with the same output value. Right? So whether you're coming into that x value of 2 from the left or the right, it is still headed towards a destination where the function is going to have a value of 1/2. Okay? However, if we are looking at the limit of this function as x goes to 0, so again, we're looking at our graph. This is the graph of our function. We want to figure out from our graph what is the limit of this function as we get closer and closer to 0. Well, you see that this part of the graph is approaching a 0 value of x from the right. So that's going to positive infinity. This part of the graph is approaching 0 from the left. However, its end destination is going to negative infinity. So because we are approaching, as we approach 0 from the right and the left, because they are getting closer and closer to a value that is different, and coming in from 0 for the right, we're going to positive infinity. Approaching 0 from the left, we're going to negative infinity. Because those are 2 different values, then the limit for this function is DNE, which represents does not exist. So from this example, you can see that it is possible that a limit does not exist for a function if it approaches a particular value. Okay, so here again we are looking at the same function, but we are approaching the limits in different ways. And depending on the function, you may have a limit that does not exist. Alright, so I'm going to stop this video here right now, and we're going to continue on to the second video. So please move on to the second video of this lesson.